Hello and welcome to another math video. Today we are going to be talking about linear functions and slope-intercept form. So we do want to be able to graph linear equations and write equations for lines. That will all begin by talking about slope. So slope for a non-vertical line is the ratio of the vertical change to the horizontal change between 2 points. You can calculate slope by finding the ratio of the difference in the y-coordinates to the difference in the x-coordinates for any 2 points on the line. So here are a few different ways of looking at slope. Slope is the vertical change or rise over the horizontal change or run. Or if you do the difference of your y-coordinates, that's y sub 2 minus y sub 1, over the difference in the x-coordinates, that's x sub 2 minus x sub 1. Notice again they're saying that this can't equal 0, because if it did, then we'd be dividing by 0, which would be undefined. It can be helpful to at least visualize, if not draw out, the points that the line is on and look at what the line looks like. From there, you can just calculate that vertical change and horizontal change in order to find the slope. Here we're going to find the slope of the line that passes through these points. So starting with example A, we do pick generally which one is going to be x sub 1 and y sub 1, and which one will be x sub 2 and y sub 2. Of course, the x's have to be x's and the y's have to be y's. It does not matter necessarily which pair are the 1's and which pair are the 2's. You're going to get the same slope either way. The way that I set it up generally is just that the first one is going to be the 1's and the second one would be the 2's. In this case, my y sub 2, so remember it's y sub 2 minus y sub 1 over x sub 2 minus x sub 1. That equals the slope, and usually we use the m for to represent slope. So in this case it would be 4 minus 7 over negative 2 minus a negative 3. You do have to be very careful again with when we have negatives and subtraction combined. Make sure you're calculating that correctly. So I end up with negative 3 in the numerator and a negative 2 plus 3, so 1 in the denominator. So again, this is really negative 2 plus 3, so it's a positive 1. So really the slope ends up being negative 3. And again, those of you that have worked with me before know that I'm really interested in exact answers, not decimal approximations, and that goes even more so with slope. We really want to see that rise and run in the slope, not a decimal approximation for the slope. Now in the cases where the denominator does turn out to be 1, we will typically write that answer as an integer, not as a fraction over 1. So, but otherwise just reduced fractions for slopes is what we're looking for. Alright, so the second example, B. If you look at these points, you might notice something special, and that's why we have 3 examples, not just to do the same thing 3 times. We're actually looking at a distinctly different case here. Notice that the y-coordinates are both 1. Now, as you do a few of these, you may find that you can notice what's going to happen here when this sort of situation occurs. In this case, again, I'll go with kind of the same pattern where I've got my x sub 1, y sub 1 here, x sub 2, y sub 2 here. The numerator, however, ends up being 1 minus 1, and the denominator negative 4 minus 3. So I get 0 over negative 7. Well, again, if you need help with that, check your calculator, but that is 0. So the slope being 0, and we'll talk about what that means a little bit more later, but really what that tells us is there is no rise for our slope, which means we're really dealing with a horizontal line in this case. And then the last example, again, not just another one to do, but a different case to look at. Notice this time around, it's the x-coordinates that are the same. So if I look at setting up the slope, I'd have 1 minus a negative 3 over 7 minus 7. So this would really be 1 plus 3 in the numerator, so 4 over 0. Again, if you need help with that, check your calculator, but that will tell you that there is an error because you cannot divide by 0, so this slope is undefined. And again, what that means is there's a rise, but there's no run. So we have vertical change, but no horizontal change. and so it's a vertical line, but the slope is undefined. And there's a few problems at the bottom of the slide there for you to try on your own, so if you want, go ahead and give those a shot. We can tell a lot about a slope just by looking at it. So if a line rises from left to right, that is a positive slope. If a line falls from left to right, that is a negative slope. A horizontal line has a slope of 0, and a vertical line has an undefined slope. So just 4 things that we can remember about slopes that we can figure out fairly quickly. If we're looking at a function whose graph is a line, that is a linear function. You can represent a linear function with a linear equation. They give the example y equals 6x minus 4. When we were looking at a solution of a linear equation, that's any ordered pair, x and y, that makes the equation true. And really when we're graphing a line, really all we're doing is showing all of the ordered pairs that solve that equation. So when we look at a line like this one, every single point on that line is an ordered pair, x and y, that makes that equation true. Special form for a linear equation is called slope-intercept form, which this equation is actually in. An intercept for a line, or of a line, is a point where a line crosses an axis. So the example they have here shows the x-intercept and the y-intercept. Again, the x-intercept is where the line crosses the x-axis. The y-intercept is the line or point where the line crosses the y-axis. So slope-intercept form, hopefully you're familiar with this already. We use it quite a bit. Y equals mx plus b, where m is the slope of the line and 0b is the y-intercept. Sometimes you might just see it written as b equaling the y-intercept. When you're talking the y-intercept, the 0 is implied. However, kind of nice that they are very clear on that the y-intercept has an x-coordinate of 0. And in that form, x and y are still just variables. So here we're going to practice writing linear equations. The first example, if you are given that 1/5 for the slope and the y-intercept of 0, -3, really you're told absolutely everything you need in order to come up with the equation. So the slope m is 1/5, so 1/5 x. Y-intercept really a -3, so -3, and then we get our equation. So really once you have that slope and y-intercept, you can write the equation in slope-intercept form. For the second example here, they just give us a graph. They do a nice job of marking a couple points so we know exactly where those are. It looks like one of those points is at 0, 4, so that tells me that my y-intercept, or b, is 4. The other point is down at 1, 1, and I can look at the slope there since it's already drawn out, and I can see I go down 3, right 1, so the slope would be -3 over 1, or just -3. And so the equation ends up being y equals -3x plus 4. And if you look here, again, a couple of examples that you can give a try to see if you can make sense of those and get those correct. Alright, next we're going to take a look at writing equations in slope-intercept form given an equation in a different form. And then once we do that, also identifying the slope and the y-intercept. So again, really trying to get some practice working with these equations and going to that slope-intercept form. So our first example, 5x minus 4y equals 16. Again, if we're going to get it into slope-intercept form, we need to know what we're aiming for. We're aiming for y equals m times x plus b. So really we're trying to solve for y. For the example A, I would probably begin by subtracting the 5x from both sides. So I'm just going to go ahead and finish that step. So if I subtract 5x from both sides, I get a -5x plus 16. Now remember, -5x and 16, they're not like terms, so I cannot combine them. From there, I have a -4y, which is a bit of a problem because I want just a plain y. Although problems are fun to solve, so all I have to do to solve that problem is divide both sides by -4. Now on the right side I need to divide that whole sum by -4, so both the -5x and the 16. So I'm going to kind of do that separately. I'll have -5 x over negative 4 plus 16 over negative 4. And a lot of times you might just skip that step, but I want to be very clear about what I'm doing there. The negatives will cancel here, so we have 5/4 x. Now notice I am writing that more in the slope-intercept form by having that be 5/4 times x rather than 5x over 4. And then the 16 over negative 4, that's going to actually end up being a minus 4. So the slope, or m, is 5/4. The y-intercept, or b, is negative 4. Looking at the next example, we do have some fractions. It might be tempting to try to eliminate those fractions by multiplying both sides of the equation by 4, which you certainly could do. However, in slope-intercept form, we're going to have to deal with some fractions, so it might just be best to kind of get used to dealing with that. But like I said, if you wanted to multiply by 4, you could. I think I will actually begin by adding 3/4 x to both sides of the equation. That leaves me with 1/2 y equals 3/4 x minus 1. Now I do need to take care of that 1/2. Now the number one thing I do not want you to do here is to divide by 1/2. Okay, do not do that, please. That's going to make a mess of just about everything. Much better way to do that when you're dealing with a fraction like that, remember you can always multiply by the reciprocal rather than dividing by the fraction itself. So multiplying by 2 is going to be a much nicer way to deal with that 1/2 than dividing by half. Dividing by half, you're going to get fractions and fractions, which is kind of a mess. So multiply by 2, the reciprocal of 1/2 instead. That gives us the single y that we want. Now I do need to distribute the 2 over this subtraction. So 3/4 times 2, again remember when you multiply something like a 3/4 by 2, you're really just multiplying the numerator, because 2 is the same as 2 over 1, so that's 6 over 4, which reduces down to be 3 over 2. So I'm going to jump right to the 3 over 2, and there's other ways you can think of that, but that certainly gets the job done. Hopefully you don't need to rely on your calculator to tell you what 3/4 times 2 is. And then the slope, again they want us to identify the slope and y-intercept. So slope is 3/2, y-intercept negative 2. And again there's a couple problems at the bottom there if you want to give those a shot on your own. Alright, so next taking a look at graphing some linear equations. At this point I want to go over a couple different ways to do this. The first one, which you're probably going to move towards, is just writing the equation in slope-intercept form and then using the slope and the y-intercept to graph it. So this first example, fairly straightforward. In order to get it to slope-intercept form, I just add 2x to both sides. So we get y equals 2x plus 1 there. So the slope being 2 and the y-intercept being 1. Now, sometimes people get confused with this. Again, your slope is your rate of change. It does not tell you specifically any actual points that are on the graph, but the y-intercept does tell you a specific point. The y-intercept, again, is the value of y when x is 0. So that tells us that the line will cross the y-axis at 1. Now see if I can get this in the right spot. Sometimes it's a little tough to graph points on this. It looks like it turned out pretty well, so we got 0, 1, that's our y-intercept. Now, once you have a point, then you can use the slope. And remember, 2 is the same as 2 divided by 1. So really I have a rise of 2 and then a run of 1, so I go up to right 1. And I can continue that same pattern up to right 1 for as long as I need to. I don't necessarily need to do this over the whole graph, but sometimes it's kind of nice to do that. Now I can also move to the left. Notice what I'm doing here. I'm going down 2 and left 1. So sometimes you want those points to move to the left instead of to the right. Maybe you're curious about what happens on the left side. So you can do that as well. And again, I did way more points than I really needed to, but you can see how that extends over the whole graph. And so that's what that line would look like when we graph it. Now again, each of those ordered pairs solves that original equation, negative 2x plus y equals 1. That's what we're graphing, is the solutions to that equation. Now an alternate method that I won't go into too great a detail here would be just to take and find values or ordered pairs that solve that equation. One way you might do that is maybe you find what happens when x is 0. Well, you could plug a 0 in for x, you find out y is 1. You might look at, well, what happens when x is 1? Well, you plug a 1 in here, you get negative 2, you add the 2 to both sides, you find out that y is 3. So you could certainly use that method, and you can use that method for really any equation with two variables. Just pick a value for x, plug it in, find the corresponding y value, and you'll be able to plot enough points to figure out the shape of that graph. So even if you forget the tricks about how to graph, you should be able to solve or graph by solving ordered pairs that solve the equation. Okay, in this next example, 4x minus 7y equals 14. Again, I'd probably start by subtracting the 4x from both sides, which if I do that here, I would have negative 7y equals negative 4x plus 14. So again, all I did there was subtract the 4x from both sides. Next, I would divide by negative 7. Now remember, when I do this on the right side, I have to divide the whole side by negative 7. That means both the x's and the 14 there. So I end up with 4/7 x, and then this will be minus 2 because the 14 divided by the negative 7. Again, on this one, my slope is 4/7. Y-intercept is negative 2. We always, always, always start with the y-intercept. Again, that's really the point 0, negative 2. So I can plot that point here at 0, negative 2. Now in this case, the slope is going to cover quite a distance. If I go up 4, so up 4 to here, and then right 7 to here, then that's where my point is. Again, that x there, just kind of a guiding tool. Help me keep track so I can get rid of that now. Now, if I'm going to try to go up 4, right 7, again, I'm going to run out of room on my graph. But I could go down 4, get to here, and then left 7, and get a point here. Again, if I try to go any further, I'm going to run out of room on my graph. Again, I can get rid of that x. It was just there to help guide me. Especially with a big slope like that, I like to have points on either side so that my graph is as accurate as I can reasonably get for doing that. Then we draw a line through there, again, as best we can. No need to use a straight edge or anything, but it should look pretty decent. Again, we've got some questions here at the bottom for you to give a try to see if you can handle those. Otherwise, I hope this was helpful, and thanks for watching.